All right, class, welcome back. So in our last session, we figured out how to get words into the machine's world by turning them into these high-dimensional vectors, or embeddings. But honestly, that's just the starting line. Today, we're diving deep into the core engine, the part of the machine that takes those static numbers and gives them life, gives them context. This is where things get really interesting. So let's kick things off with a problem, a really fundamental one. Every word starts as a vector, right? It's just a set of numbers pulled from a massive lookup table. But here's the catch. That initial vector is totally blind to context. It's the exact same set of numbers no matter how the word is used. And that, as you can imagine, is a recipe for some serious confusion. I mean, just look at the word mole. In one sentence, you've got this furry little animal digging up a garden. In another, you're in chemistry class talking about Avogadro's number. And in the third, you're at the doctor's office. We have three identical words, but three completely different universes of meaning. So clearly, context isn't just a nice to have, it's everything. And that right there is the core mathematical puzzle we have to solve. The starting vector for mole is identical in all three of those cases. So how in the world does the model figure out which mole we're actually talking about? How does it resolve this ambiguity? The solution is, well, it's just brilliant. Instead of treating each word like it's on its own little island, the model gives them a way to communicate with each other. It's a mechanism that lets each vector look at its neighbors, gather some clues, and update itself. You can literally think of it as the words having a mathematical conversation to figure out what's going on. And this powerful mechanism has a name: self-attention. Now, I really want you to absorb this. Self-attention isn't just some feature or a minor component. It is the absolute heart of the transformer architecture. It's the secret sauce that powers every single modern large language model you've ever heard of. So put simply, self-attention lets every single word in a sentence look at every other word and ask a very basic question. Hey, which of you guys are the most important for understanding my meaning in this specific spot? It's this incredibly dynamic, real-time process of building up context from scratch for every token. Now, you're probably thinking, this whole process of words talking and building context sounds incredibly complex. And conceptually, it is. But here's the kicker, the absolute breakthrough. All of this boils down to one simple, powerful operation: matrix multiplication. And this, students, is why LLMs are even possible today. GPUs, the graphics cards in gaming PCs, are absolute beasts at doing matrix math. They can run millions of these calculations in parallel, all at once. That parallelization is the key to scale. It's what allows us to build these enormous models. All right, so we know it's all just matrix multiplication, but how does that actually create meaning? Let's peel back the layers. The best way to visualize this is to think of it as a really elegant question and answer system that's running for every single word at the same time. Let's get our hands dirty with a very simple example. Imagine the phrase is a fluffy blue creature. Our goal here is pretty straightforward. We need the vector for the word creature to somehow absorb the information from fluffy and blue. It needs to learn that it's a fluffy blue creature. This whole Q&A dance happens in 3 steps. And remember, the wild part is this happens for every word simultaneously. First, each word creates a question. Second, each word provides a potential answer. And third, the model finds the best match by scoring the connection between every single question and every single answer. So let's break down step 1, asking the question. How does a word do that mathematically? Well, we take its original embedding vector, and we multiply it by a special trained matrix we call W_Q for query. The result is a new vector, the query vector. This is the mathematical embodiment of the word's question to the rest of the sentence. So, back to our example. The query vector that comes from the word creature is basically asking a question. If you could translate that math into English, it would be saying something like, hey, I'm a noun over here. Are there any adjectives nearby that are telling you what kind of noun I am? Okay, on to step 2, providing an answer. This works in a very similar way. At the exact same time, we take that same initial embedding for each word, but this time we multiply it by a different trained matrix, which we call WK for key. And what pops out? You guessed it, a key vector. You can think of this key vector as a word's name tag or its public profile. It's advertising what it can do. So the key for the word fluffy is basically broadcasting out to the whole sentence, hey, I'm an adjective. My job is to provide descriptive information. It's the answer it has ready for any question that's looking for a description. So this is where it all comes together. For every single word, we now have a question, which is its query vector. And for every single word, we have an answer, its key vector. Now for the most important step, how does the model mathematically figure out which keys are the best answers for a given query? And the answer, once again, is a wonderfully simple and efficient tool straight from your first linear algebra course, the dot product. In vector math, there is simply no better way to measure how much two vectors are aligned, how much they're pointing in the same direction. It's the perfect tool for the job. When you calculate the dot product between a query vector and a key vector, you get just a single number back, a score. And it's super intuitive. If that score is a big positive number, it's a strong match. The question and the answer are aligned. If the score is close to 0, it means they're unrelated. It's that simple. And you can see it right here in action. When the query from creature gets compared with the keys from every word in the phrase, look at what happens. The dot product scores for Fluffy and Blue are much, much higher than for the others. The model has just used basic geometry to confirm that they are highly relevant. Now I want you to just zoom out for a second. The model does this for every possible combination. The query from word 1 is compared to the key from word 1, word 2, word 3, etc. Then the query from word 2 is compared to all the keys and so on. What you get is a big grid of these scores, a complete map of who pays attention to whom. We call this map an attention pattern. So what we've just created is a quantitative blueprint for context. This attention pattern is, in essence, a precise set of instructions, telling the model exactly how information should flow between words to build up a richer meaning for each one. But this brings us to our final question for today. We have this grid of raw scores. Some are high, some are low, maybe some are even negative. They're not yet clean, usable weights that we can use to actually mix the vectors together. So how do we transform this raw attention pattern into a precise recipe for updating each word's vector? That, my friends, is the final piece of this puzzle. And it's exactly what we're going to dive into in part 3. We'll introduce a very clever mathematical function called the softmax operation that tidies up these scores and completes the self-attention